Hello everyone, welcome to the first lecture of Math 120. So in this lecture, we'll talk about geometry and algebra of vectors, which will set the foundations for the later chapters, which we will focus on how to combine vectors to get matrix. The learning objectives for this lecture is that after this lecture, you would be able to, hopefully, you would be able to understand vectors and perform basic vectors operations, which includes scalar multiplications, vector additions, and vector subtractions. You could be able to express a vector in terms of unit vector and understand the idea of linear combinations of vectors. Right. Before we go into the details of vector operations or unit vector or linear combinations, we need to understand what scalars and vectors are. So the definitions I would like to give you over here is for scalar. It's a physical quantity that have only magnitude. The example for this type of object, right, of scalar is you can talk about the distance from point A to point B. You can talk about the pressure if you apply a pressure on certain object, or you want to measure the temperature, right? Those distance, pressure, and temperature, those are scalars. So in this case, the examples are distance, pressure, temperature. In addition to scalar, we need to understand what vectors are. Vectors are physical quantity that have both magnitude and directions. So vectors is a physical quantity, magnitude, and directions. So one of the very classical example is the velocity of some object. If you want to drive your car from home to school, you need the distance, right, which is the scalar from home to school, and also the directions that you want to go, right? In this case, is from home to school. In general, this is what you use to describe a vector. Right. So this vector is required two things. Right. You have the starting point right here. This is called the initial point. And the end point right here is called the terminal point or the head. The initial, another name for initial point is called the tail. Right. So in writing, because you cannot use bold-faced letter, usually we use the arrow on top of the letter to indicate the vector. So in this case, vector V has this form, right? And because V is composed of 2 points, the initial point and the terminal point, let's say the initial point in this case is A and the terminal point is B. So this particular vector V is also can also be able to describe as AB with the arrow on top to indicate that is a vector from A to B. So given 2 points, the initial point and the terminal point, we can actually calculate the value of the vector. So that is the next definitions that we need to look at. So the component form of a vector. So let the vector V be a vector with initial point. So in this case, the initial points are u x sub I, y sub I, and the terminal point x sub t, y sub t, right? The sub t to indicate that is the terminal point. Then the vector v is expressed as v equal to x sub t minus x sub I and y sub t minus y sub I. By doing this, we can calculate the value of the vector. So let's take a quick look at the example to apply this new concept that we just learned about the component form of the vector. So given 2 points, the initial point A equal to -1, 2, and the terminal point B equal to 3, 4, the vector AB is equal to, right, because you go from the initial point A to the terminal point B, so you take 3 minus -1, and for the second component, 4 minus 2, now you have a vector of the form 4, 2. So this is the vector AB equal to 4, 2. There's a few things that you need to know in terms of the notations and how you can actually plot it or sketch this vector on the coordinate system. So in practice, you can either use parentheses like this to indicate vector. In addition to that, you can also use brackets, right, to indicate vector. Right, so this is again is equivalent to using the parentheses as vector. It's very similar to the concept of a point. When you write in a point, you use parentheses, or you can use these notations to indicate the vector as well. The vector 4, 2 indicate that so the first component is equal to 4 and the second component is equal to 2. So let me make a quick note here. So this is the first component. And 2 is the second component. And because we're talking about just 2 entries here or 2 components, the vector is in something called R2, right, or 2-dimensional vector. So that is the idea of the component of vectors. Now, if you want to sketch the vector on the xy plane, because we're talking about 2-dimensional vector only, what we can do is we start with the initial point at -1, 2, and end with the terminal point at 3, 4. So when a equal to -1, 2, the point is, so x equal to -1 and y is equal to 2. So this is the point A. The terminal point is 3, 4. And then you connect these 2 points together. Remember, A is the initial point and B is the terminal point. But however, sometimes you are given a vector with just the component form, right, without knowing the initial point or the terminal point. So it's a little bit harder to pinpoint exactly the initial point or the terminal point. Therefore, you can draw this vector that you are given in the standard positions. What do I mean by standard positions? Vector in standard position is where the initial point is at the origins. So from here, if you want to draw this vector 4, 2, right? So assume that we have a vector A equal to 4, 2. Without knowing, let's say assume at this point, without knowing the initial point and the terminal point, well, how could we draw this, right? So we start with the origins, and when the vector start at the origins, this is called the standard position. Okay, so because this is at 0, 0 or the origins, you can draw this vector at the component 4, 2. So x is equal to 4 and y is equal to 2. So these two vectors, the one in blue and the one in red, are actually equivalent to one another. In fact, they are parallel to one another. So this vector 4, 2 is in standard position. So moving on, For a vector, two things that you need to know. First of all is the magnitude or the length of the vector. The second one is the directions of the vector. So far we look at kind of the directions of the vector, going from the initial point to determine the point. Now we need to calculate the length of a vector. Right. So the idea of the length of the vector is, or the magnitude of the vector v. Let's say v is equal to v1 comma v2 is 1. So the notation is, this is kind of an absolute value of the vector, but in this context, the these notations indicate that this is the magnitude of a vector. This is equal to the square root of the first component square plus the second component square. That's how we calculate the length or the magnitude of a vector. Another notation for this length or magnitude of the vector that can be used in practice is with the two vertical line and the vector in the middle, and with another two vertical lines. Right, so these two notations are equivalent to one another at this particular level of mathematics. But most of the time in this course, I will use these notations to indicate the length or the magnitude of a vector. All right. So for example, I want to express a vector v with the initial point -3, 4 and the terminal point 1, 2 in the component form. That means you have the first component x and the second component y. And then later, after calculate the vector, I want to calculate the magnitude of the vector. All right. So the vector v is equal to 1 minus -3, 2 minus 4. This give me 4, -2. So this is the vector. Right. Again, you can use this notation as well. 4, -2 doesn't matter. Right. And here, when you have the component of a vector, you can calculate the length of the vector. Right. So the length of the vector is equal to square root of 4 square plus -2 square. 4 square is equal to 16 plus 4. This is equal to square root of 20. You can simplify this a little bit further and get 2 square root of 5. Now you can combine different vectors together, right? That's just where we could be able to perform basic vector operations. And the first thing that we can do is scalar multiplications. And then later we have the vector additions and vector subtractions. Okay. So for scalar multiplications, I would like to consider the vector v and the scalar k. Then this scalar multiple or scalar multiplications is equal to k times v. Or in this case, I could be able to describe that the new vector that I have, k times v, is a scale version of the vector v. It depends on the value of the scalar or the constant k. You can have that k times v is in the same directions as v, or k times v has the opposite direction as v. So when k is greater than 0, k times v has the same directions as v. And when k is less than 0, you have k times v has the opposite directions as v. So take a look at this graph. Given a vector v, you can double the vector v or scale it two times the original vector, and you have a new vector which is twice as long as the original vector. Or you can scale it down, right? You have 1/2 v, which is half of the original vector. Or you can change the directions of the original vector by applying or multiply a negative number toward the original vector. And if you have the vector v written in the component form, for example, if v is equal to v1, comma v2, then the scalar multiple of v is equal to k times v1, comma v2, or this is equal to k times v1, comma k times v2. That's for scalar multiplications. Now moving on to vector additions and vector subtractions or vector difference. Right. Given two vectors u and v, you can combine them together algebraically. Right. So given u equal to u1, comma u2, and v equal to v1, comma v2, then u plus v is equal to u1, comma u2 plus v1, comma v2, and you can do the calculations component wise. So that means x component combined together and the y component combined together. So this is equal to u1 plus v1 and u2 plus v2 for the vector additions. Right, similarly, when you do the vector subtractions, what you can do, the idea is that when you have u minus v, this is equivalent to doing u plus the negative of the vector v. Right. Algebraically, you can combine the components of the vector as well. So u minus v is equal to u1, u2 minus v1, v2, or this is equal to u1 minus v1, comma u2 minus v2. In addition to the algebraic method, we can combine the two vectors using vector additions and vector subtractions using some trigonometry approach. So given two vectors, let's say in this case you have a vector v and the vector w, and the vector additions in this manner is called the head-to-tail rule. On the second pictures here, this is called the parallelogram rule. The last two pictures can be done using vector subtractions. And again, the idea of vector subtraction is that you use vector additions. The idea is that you add the two vectors together, but one of the vector is the opposite directions of the original vector. So here again, if you have u minus v, then the idea is that you do vector additions with v has the opposite directions of the original vector. In addition to the basic vector operations, we have some other properties of vectors operations. Now, let's assume that you have three vectors in a plane. You have u, v, and w, and also two scalars, r and s. Right. Here are some of the properties that are quite important in vectors calculus. That you may want to know. That will be very helpful for you down the road when we combine vectors together. So the first rule is, or the first property is the commutative property. So if you have u plus v, this is equivalent to v plus u. The associative property is that if you want to combine three vectors together, you can combine the last two vectors first and then add the first vector together. Or you can combine the first two vectors and then add the third vector later, then the result has to be the same. The third property is the additive identity property, and that means when you add a zero vector, you obtain the original vector back. Right? So in this case, zero vector here, right, has the component 0, 0. The fourth property is the additive inverse property. So that means when you combine u with negative of u, you get 0 vector back. The fifth property is the associativity of scalar multiplications. That means when you have r times s, and then multiply that with u, then is equivalent to you scale the vector u using s first and then multiply with r, or this is equal to doing the scale of u with multiplications of r and then times s later. You should get the same answer. Number 6 is the distributive property. So if you have a scalar r, multiply with two vectors u plus v, then this is equal to r times u plus r times v. So this indicates that you can do the vector addition first and then scale the new vector. Or you scale the vector u and then the vector vv with the factor r and then combine the new vectors together. For the distributive property, you have another formula here. You have r plus s times u. This is equivalent to r times u plus s times u. And number 7 is the identity and zero property. So if you have 1 times u, you get back u. And if you multiply the vector u with just 0, you obtain a 0 vector. All right. So we just went through the basic vector operations and some of the properties of vector operations. Right? So let's take a look at some example here. Right? So let v be a vector with the initial point 2, 5 and the terminal point 8, 13, and let another vector w equal to negative 2, 4. Here's other few questions that we want to look at. First, let's combine the initial point and the terminal point so that you can form a vector v in the component form and find the length of the vector v. So let's do that first. So v is equal to 8 minus 2, 13 minus 5, or this is equal to 6, 8. Right. So that's the component of the vector v. Now, if you want to find the length of the vector v, what you can do is take the square root of 6 squared plus 8 squared. 6 squared is 36 and 8 squared is 64. This gives me square root of 100 or 10. Right, so the length of this vector is equal to 10 units. All right. Now, with the new vector v and a given vector w, we can combine them together through the vector additions. So v plus w is equal to 6, 8 plus negative 2, 4. Right, so you can combine these two vectors together component-wise. You get 6 minus 2, 8 plus 4. This is equal to 4, 12. The last question is, can you combine these two vectors together? The vector 3v minus 2w. Right. So 3v minus 2w is equal to 3 times 6, 8 minus 2 times negative 2, 4. Now what you can do is you can distribute 3 into the bracket and -2 into the bracket. In other words, you can scale the vector 6a and then scale the vector -2, 4 and then combine the new vectors together. So here's what I have. This is 18, comma 24 minus -4, 8. So this means you have 18 minus -4, 24 minus a. This give me 22, 16. So the new vector we have is 22, 16. That means by scaling the vector v by 3 and subtract the scale of vector w by 2, then you have a new vector that is 22, 16. Now, moving on to the next concept, which is the unit vectors. Right. So for any non-zero vector v, the unit vector u of v is given as you have u equal to 1 over the magnitude of v times v, or another form of this formula is that the vector v divided by the magnitude of v. The length of any unit vector is always equal to 1. Right? So the length of u is equal to 1. Because u is formed from the vector v, and the vector v divided by a distance here, or the magnitude, or the length, so this is always positive. So that means u has the same directions as v. Right, so the unit vector has the same directions as the original vector, so u has the same directions. And the last point for this particular concept is that, let me call this equation star. And then the name for this equation is, so star is also called a normalization process. So normalizations. So let's take a look at the example here. So you're given a vector v is equal to vector 1, 2, and I want to find the unit of with the same directions as v. So that means you just find the unit vector of v. Right? So the unit vector of v is u equal to 1 over the magnitude of v times the vector v, given that the vector v is equal to 1, 2. So what you need to do at this point is to calculate the length or the magnitude of v. This is equal to the square root of 1 square plus 2 square, or this is square root of 1 plus 4, or square root of 5. So the unit vector is equal to 1 over square root of 5 times the vector 1, 2. So you can leave it like this. This still shows that u is the unit vector of the given vector v, or you can distribute the constant 1 over square root of 5 into the bracket to have a new vector, 1 over root 5, comma 2 over root 5. And this is the unit vector of the vector v equal to 1, 2. So the unit vector is quite important because in the coordinate system, we have something called the standard unit vectors to indicate that because we're talking about two-dimensional vectors, so the standard unit vector include two vectors. Right? So the standard unit vectors are so I had to indicate that this is the unit vector in the x directions. Because it's in the x directions only, the first component is equal to 1 and the second component is equal to 0. For the unit vector in the y directions, this is equal to vector 0, 1. So the x component is equal to 0 and the y component is equal to 1. Right. In addition to these notations, I hat or j hat, there's another notations that quite useful for us to know, and probably get used a lot in linear algebra compared to calculus, is that you have e hat 1 is equal to 1, 0, and e hat 2 is equal to 0, 1. Right, so this is kind of the new notations, the way I write it. Right, this is called the column vector. What we have written so far, right, so let's say you have e1 equal to 1, 0, and e2 equal to 0, 1. Right, these are called the row vector. This conveyed the same informations, right? You can do this for any vector for that matter. It conveys the same information. It's just that sometimes it's more convenient to write one way than the other, right? So again, this is the new kind of the new notations. This is called the column vector. What we have done so far is called the row vectors. The last concept in this particular lecture is called the linear combinations and coordinates. So if you have a vector that is a sum of scalar multiples of other vectors, that is said to be a linear combinations of those vectors. Right? So formally, what we can do is have definitions of linear combinations. So a vector V is a linear combinations of vectors v1, v2 up to vn if there are scalars c1, c2 up to cn such that v can be written as c1 v1 plus c2 v2 up to cn vn. And C1, C2, and C3, and so forth, so on and so forth, are called the coefficients of the linear combinations. So coefficients of linear combinations. So this is kind of the more general definitions of linear combinations, even though so far we just take a look at the two-dimensional vector, but the vectors that we're going to consider later on can be in 3 dimensions or can be in 4 dimensions or more generally can be in n dimensions, right? So because of that, I want to briefly introduce to you the idea of the higher dimensions of vectors, or vectors in higher dimensions. So again, if you have v equal to v1, v2, or so that is the row vector, or if it's in the column vector, it means the same thing, right? So this one is in R2, which indicate that this is the two-dimensional vector. Depends on the problem, you can have 3-dimensional vector. So v1, v2, v3. So you have 3 components or in the column vector. So this is 3-dimensional vector. Or we can have an n-dimensional vector. So in this case, let's assume that V is n dimensions, n-dimensional vector. So you have n components, so V1, V2 up to Vn. Right, so n component, or V can be written as the column vector, so V1, V2 up to Vn, and all of this is in Rn. Let's quickly recap what we have so far, right? So we just start talking about linear combinations of a vector, right? So linear combinations, so a vector V is a linear combinations of n-dimensional vector if there are n coefficients or scalar such that V is equal to C1 V1 plus C2 V2 up to Cn Vn, right? Again, C in this case are coefficients of linear combinations. And I also briefly mentioned to you about the different dimensions of a vector. Most of the time what we deal with is the two-dimensional vector, three-dimensional vectors, and a more general form is the n-dimensional vector. In terms of linear combinations, let's take a look at this following example. So the vector 2, -2, -1 is a linear combinations of the three vectors 1, 0, -1, 2, -3, 1, and 5, -4, 0. That is the case because if you get the scale 3 times 1, 0, -1 plus 2 times 2, -3, 1, and minus or adding -1 of 5, -4, 0. This is equal to the vector 2, -2, -1. Right. So again, the vector 2, -2, -1 is a linear combination of these three vectors. And you may wonder how would we possibly know how to write down 3, 2, and -1. So the process of finding these coefficients for the linear combinations of the vector will be done in the later chapter. So I'm just going to give you the example to indicate that given one vector, the vector can be written as the linear combinations of all the vectors. And how you could possibly find the coefficients, that's for a later time. So the idea of linear combination is very useful in terms of locating a new set of axes or the coordinate axis, right? We have learned earlier that for the coordinate system xy plane, you have a standard unit vectors, right? So E1 is equal to 1, 0, and E2 is equal to 0, 1, right? So that is for the standard coordinate axis x and y. But if you are given two vectors, in this case, the vector u equal to 3, 1, and v is equal to 1, 2, you can actually locate or determine a coordinate grid or for the new axis. Right? So in this case, in this particular example, what we can do is if we consider new vectors w equal to -u plus 2v then w is equal to negative of 3, 3, 1 plus 2 times 1, 2, or this is -3, -1 plus 2, 4. Right. So when you do the distribution, so negative go into the first component and negative also go into the second component. Similarly, 2 times with the first component and 2 times with the second component. Now w is equal to -3 plus 2, and the second component is -1 plus 4. So you have a new vector is -1, 3. So that means that in order to locate W, you're starting at the origins and travel negative U and then followed by 2V. So let me quickly write it down. So let me quickly write that down. So to locate W, we start at the origins and travel negative U followed by 2V. Right. So that means starting as the origins, you travel negative U followed by 2V, and this is where you could be able to get W. And as you can see, the grid of the new coordinate axis U and V kind of tilted a little bit because U, the vector U, has the component 3, 1, and V has the component 1, 2. So the new grid kind of tilted a little bit. Right? So U and V can be used to locate a new set of axes. Right? And we can use this new axis to determine a coordinate grid that will let us easily locate linear combinations of U and V. So that's it for this lecture. So again, let's recap what we have in this lecture. So in this lecture, we have talked about vectors, how to combine vectors together, different way to write vectors. You have row vector or column vectors. You have basic vector operations like vectors addition, vector subtraction, scalar multiplications. In addition to that, we look at different properties of vectors, how to calculate the length of the vectors, and the linear combinations of vectors. All right. Please let me know. So that's it for today. And that's it for this lecture. Please let me know if you have any questions.